Okay, so do you remember that I told you that when you put the tubes in the NMR that they spin? Okay, that's the air. They get a little for spinning so much. Okay, which protons will be the farthest downfield in the proton NMR spectrum for the structure below? Farthest downfield. I'm getting 17. Okay, we're all up there, and we all got it right, right? Almost. It's a B. Why is it B and not C? And the O, right? It's no sigh. It's next to the bromine and the O. It's affected by two things. Which one is the farthest upfield? D. Good. All right, you're getting it. You got to start somewhere. Okay, this is t-Butyl methyl ether. And I think we saw it already. Which peak is the farthest downfield? The methyl is. This is this one. And these are all the same, right? And they're this one. Well, remember we mentioned that the heights of the peaks are directly related to the number of hydrogens that make up that peak. Okay? That is called integration. Okay? It's the area under the peak. So the relative heights of the peaks are directly related to the number of protons that are a specific kind. It is independent of the concentration or the size of the NMR. It will always work out. It's amazing.
We don't have that slide.
Sound important.
Well, it'll be on your complete slide. You're going to write it down? Okay. I'm surprised you didn't really. That's an old one. It's not like I put a new one in. You have stuff on integration somewhere? I wonder if something got lost, like a page. All right, the next spectra that we're going to look at is this one. Do you have this?
Yes.
All right, so that other slide should have been right before it. Nope. Oh, well, I'm sad. All right, so this is an NMR for a compound called paraxylene. Paraxylene has this formula. C8H10. And believe it or not, this is a little bit older spectrum. I think I got it out of a book too. But these are the integrations. Okay, so there's one. And here is the other one. Okay. You can make them be connected or you can make them be not connected. Okay. I want to draw your attention to these little peaks because you might see them when you do your NMR. It's a constant battle to get rid of them. There's something referred to as spinning side bands. Okay. They are not part of your actual spectra. How you know they're spinning sideband is that as you go out from the peak, they're even on both sides. They're evenly spaced, and they're usually pretty little. If they're big, well, then more stuff needs to be done to the NMR. Okay, so now what we're going to do is we're going to figure out how many hydrogens is each of those two peaks. Okay, so this is like a method that you could use to do to figure this out on your very own spectra, okay? So what I did was I measured from here to here, okay? So I basically, I used a ruler and I extended it out, okay? And I measured that distance and it was 25 millimeters. You can use whatever unit you want as long as you use the same one. I just think millimeters is easy. Okay, so I also went over here and I measured from here to here. Again, that's going to be, I extended it out, okay? And when I measured that one, I got 39 millimeter, okay? Now I have a formula up there. It tells me how many hydrogens are in the whole structure, right? 10, okay? So what I did was then I took 25 plus 39 and I got 64. That's the total number, okay, for all the peaks added together. I know that I have 10 hydrogens. 64 divided by 10 is what? 6.4. I wasn't trying to be tricky. 6.4, but look at your unit, millimeters per hydrogen. Okay, you can also do it the other way around. You could take 10 divided by 6.4. Okay, you could do it either way. Just make sure your units work out, because watch what we're going to do with that 6.4. We're going to go back to the 25 that we measured to begin with. So we're going to take our 25 millimeters and we're going to divide by 6.4. Make sure that the unit cancels and you end up with hydrogens. Okay, that makes sense. 25 divided by 6.4 is 3.9. 3.9. Okay, the other side, we're going to do the same thing. We're going to take our 39 millimeters times 1 hydrogen over 6.4 millimeters, and that's going to cancel millimeters, so we're going to get 6.09. Okay, how many hydrogens are in my molecule? 10. Can I have 0.9 of a hydrogen? No, and probably measuring wasn't perfect, But does anybody have a problem rounding that to 4? Okay, what do you think this one is? 6. Everybody see that? Okay, that's like a good thing to do. If you look at a spectra and you have no idea where to do, figure out your hydrogens for each of the peaks. Okay, it's a nice little system you can get into, and then if you've got 1, 6, 2, that helps you figure out your structure. You can figure out the hydrogens in your spectra. I can give you some points, okay? If you leave it blank, I can't give you anything, okay? Everybody lives for partial credit, right? That is life. Okay, this is paraxylene. It might be written on your deal. Is it? Okay. Okay, do you see the hydrogens? How many kinds are there? There's 2. Okay. These are one kind, and all 4 of these hydrogens on this benzene ring are chemically equivalent. Okay, even though it looks funny because of the double single bonds, we're going to go more into that in the next chapter. Okay, so which ones are these? The 4 off of the benzene ring. Okay, who remembers anything about the shift of the hydrogens on a benzene ring? They're around what? 7. Okay, that's pretty close to 7. Okay, and these 6 are shifted because they are next to the benzene ring. Notice they're just above 2. Okay, so it's 2 times the 3 CH3. Okay. Okie dokie. So that kind of gives you something that you can do to help you figure out. Okay, so here we have an NMR, okay, and I want you to tell me which one you think is the structure for that NMR. It's not a clicker, just gonna do it together. Okay, so what are you thinking? Look at that thing and tell me what you're thinking. Anything? Anybody have absolutely no idea what to do? What do you think? Using what you know, you can figure this out. And we haven't done everything. What? You think it's A. She thinks it's A. Okay, why do you think it's A? Okay, now I'm going to point out the integration lines. Okay, because that's one way that you can figure it out. Do you see that here? And here. Okay, when you look at structure A, how many of the benzene ring hydrogens are there? How many? 4. There's 4, right? 4 hydrogens on the benzene ring. And how many are these? There are 2. So the integration, this distance should be what to this distance? No. 4 to 2. It should be twice as big. Is that distance bigger than that one? Dang. Okay, but that's why you got to look at all the clues. Okay? Does everybody see that everyone up there has how many hydrogens, or how many kinds of hydrogens? 2. 2, doesn't it? Yeah. Okay, so what are you thinking now? Which one do you think it is? Anybody else have a vote? What?
C.
C. All right, let's look at C. Okay, how many hydrogens are on the benzene ring? 4. Okay, and how many are these? 4. So the integration values should be equal, right? 4 hydrogens to 4 hydrogens. Are they equal? They're going to be right. Okay. I mean, she kind of went like that. I'm like, they're going to be right. You look at your slide that you have printed out. Don't you have that printed out? Was that one on there? Yeah. So look at them and tell me, do you think they're the same? No. No. All right, give me another one. B. Okay. What do you think about B? How many hydrogens are on the benzene? 4. How many are on the methyls? 6. So the one that's above 2 should be taller than the one that's at 7, is it? Yeah, without even, and then you could actually measure it and make sure it works out to be 4 and 6. Okay. Remember, these are going to be little puzzles. You have to come up kind of with a system to help you figure out what it is. Okay, and you got to use all the clues. See where the shift was down here? It was about 2.3. 2.3 was that shift. Okay, if you're next to a benzene ring, you're shifted to about 2.3. Okay. Okay, now there's something else, the last thing to talk about to help you decipher an NMR is the splitting patterns. The splitting patterns tell you about the protons on adjacent carbons. Okay, only the ones on adjacent carbons have anything to do with it. Okay, so if you are a carbon and you have a hydrogen and you have a proton next to you. Let's say you just have one proton next to you, okay? That proton is not the one that's flipping, you're flipping. Okay, you're the one that's flipping. The carbon that has the hydrogen on it next to you, that hydrogen at any given time could be aligned or unaligned with the magnetic field. Just one hydrogen. There's going to be one possibility, aligned or unaligned. I guess technically that's two. Okay, so if you're aligned with the magnetic field, you're going to add to it a little bitty bit. If you are unaligned with the magnetic field, you're going to subtract from it a little bitty bit. Okay, just a little bit. So you would not look like a singlet like we saw on that last slide. You would be a doublet. Okay, that's how we get splitting patterns. By where those protons on the adjacent carbons. And it's all the possibilities. Let's see what that is. Okay. Okay, so there is the N+1 rule. Now, it says generally, okay, generally speaking, the number of peaks in a signal is equal to the number of neighboring protons plus 1. Now, it's important to remember this part, neighboring protons, okay? Next door neighbors. If you're 2 carbons away, you don't get to come to the party. Only the ones that are next door get invited, okay? Everybody else has to stay home. All right, so we're going to figure out the splitting patterns for all of these compounds. Do you have this slide? You might not have this slide. Yeah, I know I added this one late. All right, I want this to go away. All right, if I have to, I'll do that. Okay. What did I do? Oh my gosh. No. Uh-oh is right. I'm just going to say that, and we're just going to pray that everything's okay. Okay. All right. So do you see, first of all, how many kinds of hydrogens are in that compound up there? 2. Okay. So they are this one and this one. Okay. That CH3 has how many neighbors? 1. At any given time, it could be aligned or unaligned. So this will look on the spectra like this. It's going to be a doublet. A doublet will look like this. Okay, they will be about the same size. How tall they are is going to depend on how you ran your spectra and how many hydrogens are making up that spectrum. How many hydrogens are making up that peak in the spectrum? Will be 3. You get that from the integration bed. Okay, I'll ask you some more questions too as we go to help you. Okay, so I'm going to erase that because I'm worried you're not going to be able to read a darn thing if I don't. Okay, so this hydrogen has how many neighbors? 3. Okay, so here's your possibilities. What are the possibilities? We have 3 hydrogens, okay? And the arrow is going to stand for a hydrogen. We could have all 3 aligned with a magnetic field. Or we could have all 3, what? Unaligned. Let's do the easy ones first. Okay. Now, what else could we have for possibilities?
Up, down.
Up, what do you want to say? Up, down, up. That's 2 aligned and 1 unaligned. And do you see that you could have that more than that way? That you could have up, up, and down. And you could also have down, up, and up. So we would have 2 aligned and 1 unaligned. And all 3 of these are going to have the same energy. Okay, what's the other possibility going to be? 2 unaligned, 2 down, and 1 up. So we're going to go down, down, up. What else? Down, up, down. And the third one is going to be up, down, down. So we're going to be split into what's called a quartet because there's going to be how many peaks? 4, okay? But look at what it looks like. It is going to be 1 to 3 to 3 to 1. That's how you get the 3, because there's 3 possibilities. Is it always perfect? No, but it's pretty good. Okay? Because in the probabilities of life, things don't always do what they're supposed to do. But it's going to be like this. If you have a quartet that looks like this, that means something else. Okay? That's not a regular quartet. Your quartets will always look like that.
What is this for? Where did the look?
They came from only having 1 possibility.
So are they those
Okay.
little peaks that you were talking about? The
What?
spinning sideband?
No, no, these are a whole nother realm of peaks that we haven't seen yet. Okay, so like what is the next NMR that you have on your sheet? Like if you look at your slides. Okay, this one. Okay, do you see that these peaks are not pretty singlets? Okay, that's what we're doing. We're figuring out what those mean. Okay. D means doublet. I'll write it so that we get it up here once. Okay, so this one is a Q. Q for quartet. Yeah, it's not duet, it's doublet. Okay. All right, let's go over here to this one. This, how many kinds of hydrogen? How many? 2, right? This one and this one. Okay, I'm gonna pray that doesn't mess life up. Okay, so let's look at the first one. How many kinds of hydrogens does it have? How many neighboring hydrogens does it have? Just 1. So it should be a doublet. This one over here has how many neighbors? 2. So what do you think that's going to be? Okay, so we're going to have, and what do you think it's going to look like? I feel like I should be drawing all these little bills on them. Okay, so here's 2 hydrogens are your neighbors. You can be both aligned or both unaligned. Okay, what's in the middle? 1 up, 1 down. Okay, or 1 down, 1 up. So your triplet is going to be about approximately what ratios? 1 to 2 to 1. So that's what it'll look like. We're altering the magnetic field that the protons next to us are seeing by a small amount. They're going to come right by each other. It's not like they're going to be spread out over the whole spectrum. They're going to be right there. So this one is going to be a T for triplet. Okay, of those 2, the doublet and the triplet, which one do you think should be farther downfield? The doublet or the triplet? Why? No, not because it's littler. It will be littler though. It will be. It's because it's got what? 2 chlorines. Okay, and it will be smaller than the other one. Okay, up on here, these 2, the first 2 we did, which one would be farther downfield, the methyl or the CH? The CH, because it's got 2 chlorines on it. Okay, now let's go down to this one. How many kinds of hydrogens are in the next one? 2. This one and that one. Okay, so how many neighbors does the methyls have? 1, so you should get a doublet. How many does the hydrogen have? The 1 hydrogen. How many? 6. So what are we going to get? A multiple, okay. Sometimes it's called a multiplet. If you have a good NMR and a crisp spectra, you can actually count them out. How many would it be? 7, okay. Have you heard of a septet? A septet has how many musicians in it? 7, okay. So I'm going to put the 7 over here. Okay, which one of those, the methyls or the CH, do you think is going to be the farther downfield peak? The CH, because it's next to the chlorine. Which one do you think will be taller? The methyls, because how many hydrogens make them up? 6. Okay, all right, what about this one? How many kinds of hydrogen are in there? How many? 1. How many neighbors does it have? 0. So what do you get? A singlet. Okay. You have to write out septet. I forgot that. Okay. S is singlet. Okay. And typically what happens is they start using M once you get above a certain number. Once you get above, like, they start using M. Okay, what do you think about these? How many kinds of hydrogen? 2, the CH3 and the CH2. Okay, so now I'm going to try to do that. Okay. All right, so how many neighbors does this guy have? 2, so you will get a triplet. Okay, it's a trio, triplet. Okay, what about the CH2? How many neighbors? 3, so we're going to get a quartet. Okay, now what about, which one is farther downfield, the triplet or the quartet? Quartet. Quartet. We're getting good. We're getting better. All right, now how about this one? How many kinds of hydrogens are in that one? 2, 1, 2. Okay, how many neighbors do the methyls have? None. So what are we going to get? Singlets. How many neighbors does the CH2 have? None. Yeah, there's methyls in there, but they're not next door. Only next door counts. So you would have 2 singlets. Which one do you think would be farther downfield, the methyls or the CH2? The CH2. All right. I'm doing this little deal. Maybe. Okay. You got these? Okay. CH3, CH2, CH2, Cl. How many kinds of hydrogens are in that one? How many? 3. 1, 2, 3. Okay, we're going to start at the left side. How many neighbors does the CH3 have? How many neighboring hydrogens? I should say better. What? 2. So what are we going to see? A triplet. Okay. How about the guy in the middle? Ooh, what? He has 5 neighbors. Okay, they're not in the same family. They're different people. All right, so what is he going to be? 5 plus 1 is 6. That's a sextet. But we're going to call it a multiplet. Okay, and we're not going to do, you could do that if you feel like it. I'll let you do it. Okay, how about the CH2 by the Cl? It has 2 neighbors, so it's going to be a T4 triplet. Okay, we got 2 triplets in this one. Which one will be the farthest downfield? The one next to the chlorine. Okay, what do we got left over here? How many kinds of hydrogens? Okay, how many neighbors does the CH3 have? 1, so it's going to be a doublet. Okay, how many neighbors does the CH have? 5. What does this mean? Remember, the chlorine is hooked there. It was so I could type it. Okay, so it has 3 plus 2, 5 neighbors. So the peak is going to be 6. Okay, I'll multiply. What about this guy? He has how many neighbors? 1. So he's going to be a doublet. Okay, so starting to mix. Now we're going to look at spectrum. Oh my gosh. All right, so here's a spectra of CH3, CHCl2. Was that one of the ones on the other slide? Okay, so we have 2 kinds of hydrogen. Okay, the CH3 has 1 neighbor, so it should be a doublet. Okay, so if you look at the peaks on the spectra, you'll see that they look messy. We don't get nice, pretty singlets like I've been purposely showing you in the other section. Okay, we don't get nice, pretty singlets. All right, do you see that there are 2 there? Sometimes that's hard to see. So what they'll do is they will do a blow up. And we can do this on R and MR, believe it or not. Okay, and so this is a blow up of this peak right here. Okay, is it easier to see the doublet there? Okay, so what about this one? That looks kind of messy, doesn't it? So they blew it up for you. Do you see that it's a quartet? Okay. If you measure from here to here and from here to here, your integration values will be 3 hydrogens and 1 hydrogen. Okay, what is this little junk? I don't know. This one is from the chloroform. This looks like something was in their sample. They publish this in the book and they don't even get a good sample. But I think part of that is so that you see that you can have a little bit of trash in there. Okay, if you have trash in your samples, a couple things to look for would be to look and see if there's acetone in there from cleaning the tube prior to using it. Look and see if there is solvent in there from when you recrystallize something. Okay, that's a common thing that I'll see. Okay, or maybe there's a little starting material mixed in there. You didn't get them separated out really good when you purified. Those would be things to look for. Okay, ethylbenzene. Okay, here is ethylbenzene. It's a benzene ring with a CH2CH3. It's an ethyl on a benzene ring. The easiest name, okay? How many kinds of hydrogens are in there? How many do you think are in there? Okay, well, we got this one. We got this one. What do you think? Are all of these actually the same? No, because these 2 are there. These 2 are 1 away from the ethyl. And then last but not least, we have 1 out here. So you look at that structure and you may be going 1, 2, 3, 4, 5. There should be 5 peaks. But when we actually run the spectrum, these are not differentiated. Okay? So that's on the next slide. This is the actual spectra of ethylbenzene. Okay? And here it's what we call a mess. That's the technical term. Usually what you do is you write complex. When you record your spectra, you'll write the term complex, or you will just write multiplet. Whatever JZ tells you, because there's numerous ways you can do it. Okay, what can you tell me about the other hydrogens? Okay, how many neighbors does this CH2 have? 3, so it should be a quartet. How many neighbors does this guy have? So it should be a triplet. Okay. Can you find them on here? Okay, so what do we have here? We have doom, boom, boom. That's a triplet. Here we have boom, 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 boom. What is that one? It's a quartet. Which one is farther downfield? The CH2, does that make sense? Because it's next to the benzene ring, okay? What's way down here are all the hydrogens on the benzene, okay? There is a cute term for that. It's called accidentally equivalent. It just turns out there isn't enough difference for them to be differentiated, okay? Even if you went to a bigger NMR, you just get more mass, okay? So those are not going to have a specific splitting pattern, okay? So anytime you have a benzene ring where you have 5, hydrogens, and you have something here, I'll just put X for anything. All 5 of those are going to pretty much come together on top of each other, okay? Even though they are different hydrogens. There are 3 kinds of hydrogen there, but you're only going to get one area where there's going to be peaks, okay? And okay, this is isopropyl methyl ketone, okay? Who remembers what a ketone is? You have a carbonyl and you have an R group on both sides. So isopropyl means on one side we have an isopropyl group, and methyl means on the other side we have a methyl. Okay, how many kinds of hydrogens are in that structure? 3. Okay, now look at our spectra. How many kinds of hydrogens do we have? 1, 2, 3, right? Okay, what is the splitting patterns that you would expect? How many should this be? How many neighbors does it have? 1, so it should be a, this one has how many? 6, so it should be a multiplet. We'll just go with that. What about that CH3 on the right? Does it have any neighbors? No, so what should we see? A singlet. Okay, can you see them all? Okay, so, and if you look down here, this little one that's split with all those hydrogens, okay, they blew it up. So you can go 1, 2, 3, 4, 5, 6, 7. And I did touch the right peaks, not that the dots went in the right spot. Okay. Notice this is our singlet and here's our doublet, and they even did that for you. Okay. What should the integration values be? So the blue line is the integration. Notice that from here to here, that's 1. This is 3 times this, and this is 6 times that. Okay? Or you can take your formula, which would be C 4 H 3 6 9 10 O. Okay, and you could go through and measure them all and do the division and figure out how many hydrogens is in each peak. Because do you think you're going to be given 1, 3, 6? Not necessarily. Okay, is that making sense? All right, let's see. Does that go away? Okay. And I have written A, B, and C. I want you to notice which one is farther downfield. C is farther downfield than A. Okay, even though they're both next to the carbonyl, you'll still notice they're pretty close. But remember way back in the dark ages of Monday that I showed you some shift values, and the carbons that are more highly substituted, those hydrogens were a little farther down. So that's where it's coming from. Okay. Okie dokie. How you feel about that? You might not know. Okay. A coupling constant is the distance between the peaks within a splitting path. It is often referred to as the J value. The J value. Do you have this? Okay. It is again independent of the operating frequency of the NMR. You can take your peak if you need to, and you can blow it up and you can measure that number. You can get that off our NMR. Okay. It's not something I do very often. You would only do it if you were trying to figure out some really unique things, or it's not something that I do every time I get a spectrum. Okay, I only do it if it's special. Okay, so look at this compound. This is 1,3-dibromopropane. Okay, notice that there are how many kinds of hydrogens in that? 3. Does everybody agree that? Ooh, that you should make sure that you're on the pen before you move. Okay, that these two are the same. Do you see the symmetry in there? Okay. The peak in the middle, A, has how many neighbors? 4. So what do you think you're going to get? 5. Okay. 1, 2, 3, 4, 5. Okay. The peak on the outside, the B's, they have how many neighbors? 2, so we should get a pretty little triplet. Okay, there it is. Okay, this one is 4 hydrogens, and this one is 2 hydrogens. Notice the ratio is 2 to 1. That makes sense. Okay, do you agree that the B's should be farther downfill?
Yes.
Yes. Okay. All right, look at this compound. Now we're getting more complicated, aren't we? This is isobutyl butyrate. No, isopropyl butyrate, my bad. Okay, and look at how many kinds of hydrogen. 1, 2, 3, 4, 5. Okay. All right, so look at these. Who is the farthest downfield? If you look at the structure, which one do you think should be the farthest downfield? The one next to the O. Okay, E. And E has how many neighbors? 6. Okay, so looky here. There it is. Okay, it's little. It's little. It gets even smaller when you put it on a piece of paper than on the screen. All right, and looky here. 1, 2, 3, 4, 5, 6, 7. They're all there. Okay, we're not going to be sneaky and not give you blow-ups if they're available. We're going to give them to you. The only way to get good at looking at NMRs is to do what? Look at NMRs. Okay, so pull out your book and start looking at NMRs. Okay, all right, so what do you think this one is? That's a blow up, but which one do you think it's a blow up of? Well, look at the scale underneath here. What does that say? 1.2, so it's a blow up of this one. Okay, that's B's. Those are the B's. Okay, which one is peak C? How many neighbors does C have? 5, so it should be a 6. Which one do you think that is? This one right here. Do you see how many peaks there are? This one is a what splitting pattern? A triplet, so it has 2 neighbors. I'm going to use a little n for neighbor, not neutral. Okay, this one is a triplet, so it also has 2 neighbors. Which one is the peak above 2? D, because it's affected by the carbonyl. Okay, getting a little better? I mean, really, it takes practice. It's going to be a puzzle because what's going to happen is I'm going to give you one of these, and I'm not going to give you the name. I'm going to give you the formula, and you're going to figure out structure. Okay? Are you scared? Slightly. It's not so bad. It just takes practice and a system. All right. Now I want you to tell me what is the splitting pattern of the indicated proton in the proton NMR spectrum. The one that has the arrow by it. Remember what the letters stand for. D is doublet, S is singlet, T is triplet, Q is quartet, and what's the little M? Multiplet. Okay. There's a couple little things I'm going to show you, and we're going to do some unknowns. Okay, where we're going to start from the NMR and the formula. Okay, but I have a couple little things. I talk about OHs and NHs, the odd polar. Okay. All right, we all got it, right? How many okay, I'm pointing to the CH2, right? How many next door neighbors? 1. 1 plus 1 is? So it's a, okay, you don't count the ones that are on it. You count the ones next door. Okay, the ones next door. Okay, how about that one? You put G?
No, I changed it. I thought it was.
Okay, okay. That's happened. All right, are we there? Okay. Woohoo! How about this one? You gonna get 17? Only got 16. Nobody snuck out, did they? All right. Okay. How many neighbors does this guy have? 1. What is it? Doublet. Okay, doublet. Okay, let me draw it out like this. First of all, do you see that those 2 methyls are not neighboring each other? Okay, I wasn't trying to be tricky. Okay, this is the only one that's neighboring them. Okay, because I think that was how come somebody picked Q. Do I have one more? Surely I have one more. No, okay. Darn, I thought I had that CH3 on the right. But you got it now, right? So at the beginning on Friday, I'm going to ask you a splitting question.